We back. Getting mixed messages. No. So I mean, at some point, definitely go back and watch yesterday's stream. But for right now, what we're talking about yesterday doesn't mean that you can't understand what we're talking about today. Right. So I mean, for the warm up, you won't know how to do the warm up, but that's okay. Right. The rest of the stuff, you won't need to know yesterday's knowledge specifically. Haha hat. Yes. Today's stream sponsored by Teague Electric Company. Make sure you use them to purchase all your construction and lighting needs. It protects my head from the virus, you know? Smart. Why do you have so much Teague merch? Because my dad works for Teague. And I always ask him what free stuff he has. And I really hope that he'll sponsor me one day. Okay, so for the warm up, which of the following series converges to 2? All right. Yesterday, we talked about nth term test, geometric series test, and telescoping series. Test. Well, I do really like Teague, you know, because my dad works there. So whatever. So which of these converges to 2? For my first, the 2n over n plus 3, I'm going to first try my nth term test. So this is an. So I'm going to look at the limit as n goes to infinity of an. That would be infinity over infinity, an indeterminate form. So I'm going to take the derivative. Two over 1. So 2. Now, that should tell me then that number 1 is not my answer. Okay. The limit of the sequence is 2. Right? If I take the limit of an, it is 2. But from yesterday, our nth term test tells us that if we get an actual number for the limit of the sequence, that tells us then that the series diverges. Okay, so if the sequence converges to something other than 0, then the series diverges. That is the nth term test. All right. So for number 2, -8 over -3 to the nth power. So again, if I look at this, this is my an. So let me look at the limit. That denominator will just be increasing while my numerator stays -8. So this limit goes to 0. Okay, and also from the nth term test yesterday. So again, if our limit is something other than 0, then we know that it diverges. However, if our limit is 0, then the nth term test is inconclusive. This series could converge or diverge, right? We're not sure exactly. We'd have to use some other type of test. But so for the second one, this is not in the form, it's not a geometric series, and it's also not a telescoping series. So as of right now, I just kind of feel stuck on number 2. I'm as far as we know, it's not. And just looking at it, it seems hard to believe that it could converge to 2. But so let me go on to the third option. All right, I'm going to rewrite this. Right? So I just put the n on the outside because exponent rules, 1 to the nth is always just 1. So 1 over 2 to the n is the same thing as 1/2 to the nth. Doesn't matter. And this is almost in the form of a geometric series. So notice that this series, it says, is starting at 0. To be a geometric series, it would need to start at 1. So let's rewrite it so that it does. So I'll start it at 1, but if I bump that starting place up 1, then I need to account for that in my exponent. So instead of my exponent just being n, my exponent will be n minus 1. All right, that way, if the first number I plug in is 1, I still get that power of 0. Like the first series, the original series wants me to plug in 0 first. So that's fine. I can just rewrite it like this so that it does go from 1 to infinity, and the first number I still plug in will be 0. So 1/2 n minus 1. So 1 minus 1 is 0. And then plus 1/2 2 minus 1, 1. And then etc., etc. Okay, so I've just manipulated it and I've changed it so that it looks like it's in the form of a geometric series. Right? And so a geometric series, whatever's in the parentheses, that's my ratio, r. The absolute value of r, so the absolute value of 1/2 is 1/2, which is less than 1. So we know the series does converge. Right? The series converges since we see that that ratio is something, the absolute value of the ratio is less than 1. And what does it actually converge to? What is the sum? If I added up all those, the 1/2 to the 0th, plus 1/2 to the first, plus 1/2 to the second, plus 1/2 to the third, etc., etc. So we had a formula for that, which is a over 1 minus r. So a, in this case, the coefficient is just 1, the first term. Right? A also represents the first term, and we can see up here, 1/2 to the 0th power, the first term is 1. And 1 minus 1/2 in the denominator. 1 minus 1/2 is 1/2. 1 divided by 1/2 is 2. So that third series is what converges to 2. Because it is a geometric series. It just didn't look like it at first, but we can see that it is. The first series we knew didn't work because of the nth term test. Since we got an actual value for the sequence, we know that the series diverges. So remember, the sequence is just like the formula part, right? A sequence is just a list of numbers. A series tells you add all those numbers up. Okay. So the sequence converges to something other than 0, then this series will diverge. All right, so we're going to talk about our next tests today. All right, I told you we're going to have a lot of them. So today we're going to talk about the integral test and the P-series test. Our overall goal of this unit is to know how to test the convergence of a series. And today we're going to learn how to use the integral test and the P-series test. These would be definitely, all these tests will definitely be good things to, you know, if you're someone who does make or has the ability to like make some note cards, some like flashcards for yourself, do that. Even if you don't have flashcards or don't want to go out and get some because it's too dangerous, then, you know, I mean, cut up a piece of paper at your house and write stuff on the front and back of it. Or you can borrow my mask if you want to go out. That's fine. Quizlet. Yes, you can use Quizlet. It's just tough to type in math stuff on Quizlet unless you pay for the premium version. But true. So first is the integral test. So this, we have to have a lot of prerequisites in order to use the integral test. F has to be positive. So the function, some function, whatever we're talking about, it has to be positive, right? Like if I look at the graph, it's all above the x-axis, for example. Continuous, okay? No asymptotes, holes, discontinuities. And decreasing. So another way to think about decreasing is that the derivative is always less than 0. So when should this be true? So as long as all of these things are true for whenever x is greater than or equal to 1. All right, so if one of these things isn't true, like if x is negative or if x is 0 or something like that, well, then that's fine. We don't care about it. As long as these things are true for whenever x is greater than or equal to 1. And we care about that because, remember, for our series and sequences, we're using the natural numbers. So we're usually starting by plugging in 1 and then going to 2, 3, 4, 5, 6, 7. So we only care about numbers that are greater than or equal to 1. Okay. So what we can say is this series and this integral either both converge or they both diverge. So if we know one, then we'll know the other. So if I want to know if a series converges or diverges, well, maybe I can look at the integral. I'll look at the integral of the sequence from 1 to infinity, and I'll see, does that converge? Does that diverge? Whichever I know the series has to do the same, assuming that all of these prerequisites are true. F is positive, it's continuous, it's decreasing, all for x greater than or equal to 1. Okay, so here's just kind of the basic setup of how this looks like, right? These first 3 steps are just the setup. It's just checking to make sure, hey, is the function positive? Is it continuous? Is it decreasing? So like I said, if we're looking for it's positive, if you need to, look at the graph to determine, oh yeah, it's all above the x-axis. State if it's continuous, so think about the domain. Make sure we're not going to be dividing by 0 anywhere. Okay, make sure there's no discontinuities or holes. And figure out that it's decreasing. So if we need to, we'll find the derivative to show, oh yeah, the derivative's negative, so it must be decreasing. So those first 3 steps are just the setup to prove that we're allowed to do this. Step 4, we'll integrate from 1 to infinity. And step 5, we'll make some sort of conclusion. Oh, hey, the integral diverges, so the series diverges. Or the integral converges, so the series also converges, right? But the point is they both have to do the same thing. So determine the convergence of the series. Justify your answer. All right. So let me run through my checks. All right, n over n squared plus 1. Anyone else having issues with lag? I don't know. Is anyone else? If a bunch of people are, I can restart and refresh everything to see if it's from me. Nope. Dang. Charlie, you at RJ's house using his internet? Come on. Get your own. Stole his Ethernet cable, man. I ordered that 3,000-foot cable off of Amazon. So our first thing we want to know is F positive? So this is our function. So this is the sequence, and that's what we're using as our function F. So would this always be positive? So again, think about 4 values of 1 and greater. Well, I don't think we could graph this if we need and look at that, but for values of 1 or greater, yeah, we're not going to get a value that's negative ever. If we're only plugging in positive numbers here, we're never going to get a negative function. So yes, F is positive. That's for sure. So that's my first check. Second check. Is it continuous? Yeah, so the only thing that could happen, I'm a little bit worried because I see a denominator initially. Because I know denominators are where sometimes now I could have a vertical asymptote or a hole showing up. But what number do I plug in to n that would give me -1? So -1 plus 1 is 0. Well, there's no number that I can square to make -1, right? It's impossible. So, or no real number. So it's continuous. I'm good there. Now, is the function decreasing? Bet. So I'm a little less uncertain just looking at it. So what I'm going to do is I'm going to take the derivative. And since this is a rational function, then I think you all know and love what we're about to do, which is the most wonderful rule of all, which would be the quotient rule. All right, so the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared, or low d high minus high d low over low squared. Okay, so n squared plus 1, derivative of the top is 1, minus the top times the derivative of the bottom, n squared plus 1 squared. So that would be n squared plus 1 minus 2n squared over n squared plus 1 squared. So negative n squared plus 1 squared. And it might help us actually. Let me rewrite this as, instead of negative n squared plus 1, I'm just going to switch the order. So it's 1 minus n squared. Okay, so this is the derivative. And let's take a look at this for a second. So let's kind of use our intuition. So my want to know is this negative always? Well, the denominator will always be a positive number, right? Because the denominator is getting squared. So I know the denominator will always be positive. Okay. And for my numerator, 1 minus n squared, so n is, something that's like 1 greater than 1. So that numerator will be negative. So if the numerator is negative, the denominator's positive. So yes, that derivative is negative. It's less than 0. You can barely see that 0, but that's a 0. So yes, this function is decreasing. Great. So once I've checked for all three of those things, now I can look at doing the actual integral. All right, so 1 to infinity of x over x squared plus 1 dx. So in solving this integral, I'm noticing that the numerator is almost the exact derivative of the denominator. Okay, so it's going back to our integration techniques. So the derivative of the denominator is 2x. Now the numerator is x, not 2x, but remember, we don't care about, we care about, but I'm not worried about a coefficient. I can fix coefficients easily, or I can move coefficients to either side. So if I make a u substitution for x squared plus 1, take the derivative and then move the 2 over to the left, bring that dx over to the right. So I can see I'll be able to make a nice substitution here because I have the x and the dx. So I'll substitute that for du over 2. And that just leaves me with 1 over u du. Hopefully, we know that the antiderivative of u is natural log. Right, then it's being evaluated from 1 to infinity. So I'm going to make a limit. I'll bring the 1/2 out in front. So natural log u evaluated from 1 to, let's say, b, so that we can actually plug in something that's not infinity. So natural log of b minus natural log of 1. natural log of 1 is just 0. Right? That's just a simple evaluation. The natural log of b, as b goes to infinity, so as I plug in larger and larger and larger values of b, that natural log function is also just going to increase. So this diverges. It goes to infinity. So the reason we did all that prep work at the beginning was to say, oh, we can use the integral test here. So since this integral diverges, then we know that our series of, what was it? N over n squared plus 1. It also must diverge. How do we know that? We know that because of the integral test. Since the integral from 1 to infinity diverges, then we know the series must also diverge because they both have to do the same thing. If we show that all three of those things at the beginning are true, then this integral and series will either both diverge or both converge. Good morning, RJ. It was a little late. We're at 9:48 and you're just now telling me good morning. That's serious slack. Oh. I said that at 9:15. Oh, I just got a puppy. Oh, that's exciting. Do you have little like gloves for it so it can stay safe? Okay. So what's the difference between sequences and series? Let's say that this AN is 13579, just the odd numbers. This is a sequence, which is just the list of numbers, basically. Okay, it's a list of terms. But the series version of this so sigma series just tells me to add all those things together. So 1 plus 3 plus 5 plus 7. Okay, etc. So sequences and series, sort of very closely related. The sequence is just what are the numbers. Series says, hey, take all those numbers and add them together. Does that make sense? Yes. Okay, cool. Good deal, Spicy Chicken 819. So determine the convergence of the series. Justify your answer. All right. So if we tried to do the nth term test on this, this limit is 0. So the nth term test tells us nothing. Right? So whenever we're figuring out if a series is divergent or if it converges, then we don't really exactly know off the top what rule we should use. We might have to use the alternating series, or the telescoping series test, geometric series test, nth term test, or now potentially the integral test. So in this case, I would initially probably start by trying to do the nth term test, but the nth term test tells us nothing if we find that this limit is 0. So that's why I would move on now to the integral test. All right, so I have to do all my checks first. So is f positive? Remember, we're plugging in numbers that are 1 and greater, right? The natural numbers. So n squared plus 1, 1 divided by that. Yeah, for sure. Those will always be positive numbers. If you need to graph it to double check, do so. Is it continuous? So again, I would be worried about the denominator, but there's no number that would give us -1 to get the 0. So yes, this is continuous. Why didn't you do the nth term test for this one? I just did. The nth term test is taking the limit of the sequence and seeing what you get. But if we get 0 when we do the limit for the nth term test, then it doesn't tell us anything. If we had gotten an actual number, like that limit equals 3, then I would be able to say, oh, I know that the series diverges. But if I get 0, exactly 0, it doesn't tell me. It could still diverge or converge. I need to use a different test. So it's continuous. Is it decreasing? Again, let's take a derivative here. So let's think about this as n squared plus 1 to the -1st power. So my derivative would be -1 times n squared plus 1 all to the power of -2. So by looking at that derivative, the denominator will always be positive because the denominator is always getting squared. And the numerator is always -1. So yeah, I feel definitely confident saying this is negative. So the function is decreasing on this interval. So my 3 checks are complete. F is positive, it's continuous, and it's decreasing whenever x or n is greater than or equal to 1. So now that means let's actually do the integral. What about the reverse chain rule? Reverse chain rule. Well, reverse chain rule would be like if we were integrating, right? Wait, reverse what? Oh, just the chain rule. Ah, yes. Just the chain rule in general. Sorry. Yeah, the chain rule in general, so we would have to multiply by the inside, so that's 2n. No, but you're right. Yeah, so bad wording, but you're totally correct. That we would need the chain rule. I was too focused on, so the same thing is still true, right? The numerator will still always be negative. the denominator will always still be positive. So it's still less than 0. I jumped ahead of myself and was too focused on the fact that it would be negative. But yeah, so we still need the chain rule there. The rope method. I always use the wire rule. String rule is not bad. The yarn rule is hit and miss, so it just depends on which one you want to do. Right, but the upside down reverse rubber band rule is still pretty solid. Crochet calculus. Okay, so now I want to look at the integral 1 to infinity of 1 over x squared plus 1 dx. Now, I don't need to tell you what integral this is, right? It's not natural log because we don't have, if we try to do u equals x squared plus 1, we would need the 2x, or at least the x in the numerator. But okay, that's just the 2. Yeah, that's just the setup for arctan. Right, the x squared plus 1. Wait, not. No, it should be arctan. No, you're right. Unless I'm now wrong, which rarely ever happens. Me being wrong sounds absurd. Never mind, I was okay. Real back and forth here. Some highs and lows. Yeah, so it should be arctan. All right, so let's take the limit. Again, let's use a replacement variable. Let's say b. From 1 to b. So arctan of b minus arctan of 1. Okay, so I'm going to start with my second piece, actually. Arctan of 1, so if I think of what angle would give, is tangent equal to 1. So tangent of what angle equals 1? It's pi over 4. And now to arctan of b as b goes to infinity. So again, sort of thinking along the same lines of tangent of what angle gives me infinity? Well, that's kind of a weird question, but the answer is pi over 2, because at pi over 2, right, our point is 0, 1, and tangent is y over x. So 1 over 0, if we took that limit, it diverges to infinity. So if I'm going the opposite way and I'm saying, okay, arctangent, so what angle tangent of that angle approaches infinity, it would be at pi over 2. So So pi over 2 minus pi over 4. I could combine those if I want, but the point is I got an actual value. So since I got an actual value, then that means that integral converges. And if that integral converges, then I know for sure that this series also must converge. And we know that through what we just did, the integral test. We had to do that setup at the beginning to prove all of those conditions are met, those prerequisites. Then once we take the integral converges, so that means the series, the original series that we started with, has to also converge. That's what the integral test tells us. So actually not a huge amount of work. I mean, I'm not implying that it's easy, but we made about 3 lines of work here. The beginning part is just doing some quick checking of making sure that all those conditions are right at the beginning. All right, so that's the integral test. Definition of a p-series. So a p-series looks like this, where it is just 1 over n to the power of p. An alternate way that this could be written is like this, because again, 1 to the power of anything would still remain 1. So we could write it the way that it's typed or the way that I just wrote it above. Both of those would be considered p-series. All right, and this is considered a p-series as long as that p is a positive value. All right, so it always has to be 1 over n to the power of something, some positive number. The p-series test is pretty straightforward. And it's just this. As long as it converges if the power is greater than 1. That's it. Otherwise, it diverges. The end. Okay, and so that's summarized down here at the bottom. So if p is a number greater than 1, it'll converge. If p is somewhere between 0 and 1, then it diverges. So definitely more simple of a rule than like the integral test is. There's a lot less to remember. As long as we recognize what a p-series looks like, then it's just, okay, greater than 1, it'll converge. In between 0 and 1, it'll diverge. Right. Determine the convergence of the series. Justify your answer. All right, well, first thing that I do when I look at this is I recognize that this is a p-series because it's just 1 over n to the power of something, and that power is positive. So in this case, p is 2, so that means it's greater than 1. So we can automatically say the series converges.
I didn't get that. Try again.
Siri really wants to talk to me. As do most people, I find, everyone's always wanting to talk to me and hang out with me and stuff. It's like I'm trying to practice social distancing. Apple user spotted. Yes. What a breakthrough. Determine the convergence of the series. Justify your answer. All right, so I have another series. This one looks a little more complicated. The Siri converges. Yeah, if I say "Hey Siri" on here, does your phones recognize it? Sitting there watching. Hey Siri. Did your phones go? Did they recognize my voice as your own? Do I need to do my impression of you guys? Right, but this series looks a little more complicated. There's more stuff going on. But again, sometimes we might have to manipulate things or change things up a little bit, like we did at the beginning. And I had to change stuff so that it actually looks like it was the form of the geometric series. So same thing here. I'm going to change this. I think I can transform this into a P series. Headphones, you nerd. Okay, well, sorry, I can't afford headphones. All right, my bad. So first thing I'm going to do, I can bring my coefficient out. That was one of the properties of series that we talked about last time. I'm going to rewrite n, so the n squared, and then the fifth root of n, I'm going to write as 1/5. So it still doesn't look like a P series, not exactly. So I'm going to keep going here. And I'm going to combine the n squared and n to the 1/5. So 2 plus 1/5. I will wait. I think we all know who should be answering here. Reese. Yeah, is Reese watching these? Is RJ lagging pretty hard here? Come on, buddy. 2 plus 1/5. Maybe he fell asleep. Well, no go. I guess he bailed on us. Uh-oh. Oh, he's back. Come on. Talking to my parents. RJ, we need 2 plus 1/5. We don't know. The new RJ. That's it. I'm coming over to your house. I'm ripping out the Ethernet cable myself. Right. I will brave the dangers of the outside world. 11/5. So this is a P series. And in this case, the value of P is 11/5, which is greater than 1. Right, so just like last time, right, going back to our rule, greater than 1, it converges. 0 to 1, diverges. So the series diverges, or sorry, not diverges, converges. And we use the P series test. I'm just going to possess RJ through the Ethernet. The ethereal plane. That one was for you, Charlie. Okay, so P series are pretty straightforward. So maybe you'll have to do a little bit of manipulation like in this one where you move some stuff around and combine some stuff to make it actually look like the form of a P series. But if you have it, if that exponent is larger than 1, then you're good to go. All right, it converges. If it's between 0 and 1, then it diverges. Just shout mixed numbers. That'll do it. Definition of the harmonic series. Okay, the harmonic series is a specific type of P series, and it is the P series whenever P equals 1. All right, so it's just the series from 1 to infinity of 1 over n. So 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, etc., 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 etc. Okay, so it's just that whenever P equals 1, we call it the harmonic series. All right, we inquire now. No, but it is related to harmonics regarding music, right, and harmonic notes, because it's based on sort of the, I don't want to get too much into it, based on kind of the wave forms and adding up these waves that create a harmonic. No, you're in a band? Sick. What band is it? Are you guys on YouTube? I heard you had to cancel all your gigs. Melodic time. Our 3 Days Grace cover band is still going to go strong. We do not care about the at the virus at all. We're still going out there, and we're still going to play. Keep the people happy. All right, we'll just have to take necessary precautions. All right. Schmitty and the Panthers. All right. Harmonic series. So since P is equal to 1, right, this diverges. That was part of our original rules, so this isn't anything different. Notice that this says if it's less than or equal to 1, then it diverges. So in the case that it is exactly equal to 1, it still diverges, but we just call it the harmonic series. Isn't there an actual answer to what it equals, though? No, there is not. It diverges. No, not for this one. Maybe something else. It is for other ones, like n squared. Like if it's 1 over n squared, then that sum, that infinite series just equals 1. It all adds up to 1. But not for harmonic. Okay. And remember, even if we see a series that looks like, you know, this. Okay, well, just think about changes that we can make. That's the same thing as 1 to the 5th over n to the 5th, or just 1 over n to the 5th. So this is a p series where the value of p is 5. 5 is greater than 1, so it converges. This is our homework. Well, actually, so a couple things. So this is the homework pertaining specifically to this section, the P series and the integral test. If you want to practice those, right? It's just those two. I also assigned you a multiple choice question progress check on the AP site. Okay, so completing that will be a checkpoint in Summit. All right, so this homework right here is just general practice to help yourself. Okay, those multiple choice questions on the AP website, completing that I will count as a checkpoint in Summit. I think it's like 10 multiple choice questions, and a lot of them are quick, like P series stuff, but it's just based on chapter 9 so far. So that's integral test, P series, geometric series, nth term test. Okay, so check that out. No stream tomorrow, right? No, I don't have a stream tomorrow planned. Okay. So make sure do this, spread this, because again, I don't know. It seems like we have most of our class here. Again, sometimes it's hard to tell because I don't know who is who, but seems like most of our class is here. But if there's anybody that you know that does not watch this stream or doesn't watch and also doesn't watch the YouTube videos, then at least let them know that this exists and that it'll be a checkpoint on Summit. That's fine. You don't know who I am either. I could be anybody. Complete anonymity. Right? I mean, I mean, who am I? All you can do is hear my voice